Something about Apophis refuses to feel simple. Its path through space has been calculated with such precision that astronomers can place it on a particular Friday evening, 4 years from now, to within a kilometer. But the object itself is far less tidy than its orbit. Its density appears too low for a single solid stone. Its rotation is strangely unsettled, and its outline suggests two masses clinging together rather than one clean body. Then, in 2029, Earth's gravity will reach out and pull on this delicate structure more strongly than it has likely been pulled in millions of years. The concern is not that Apophis will strike our planet. Scientists do not expect that. What makes them uneasy is the more subtle question. What will this fragile, tumbling object become after such a close encounter? Beneath the online fear and the dramatic headlines, that is the mystery worth following. Calm space is where we slow the story down and look at what the evidence actually says, because sometimes the most interesting danger is not impact, but uncertainty. Begin with the night itself. On the 13th of April, 2029, billions of people will have the chance to step outside and see something moving among the stars. It will not behave like an aircraft, blinking across the sky, and it will not quite resemble an ordinary satellite following its familiar silent path. Instead, a bright point will drift against the fixed constellations quickly enough for human eyes to notice its motion. It may shine more strongly than nearly every star around it, even outshining the stars that form the handle of the Big Dipper. Yet the most haunting part is that this apparent light will not be light in the ordinary sense. It will be sunlight reflecting from a rock, a body roughly the size of a skyscraper, passing Earth close enough to cross the region where some of our own machines circle the planet. That image matters because it turns an abstract orbital calculation into something visible, something people may remember as a moving mark in the dark. No known moment in recorded human history matches this one in quite the same way. Larger objects have approached Earth, and smaller ones have come nearer, but this combination is different. A body of this scale, this close, with years of warning and a global audience waiting for it. Across parts of Europe, Africa, and the western edge of Asia, the flyby will become a single evening event, not hidden in a telescope archive or reduced to a line of data. Roughly 2 billion people may be able to see it with unaided eyes, needing only clear weather and the decision to look upward. There is something quietly profound in that. For once, a near-Earth asteroid will not be merely a scientific bulletin. It will become a shared human sight. The distance involved is hard to feel, so it helps to compare it with the structures we already understand. At closest approach, Apophis will pass about 31,600 kilometers above Earth's surface. That places it inside the region of the geostationary satellites we rely on every day, the spacecraft that support television signals, weather information, and much of modern communication. Those satellites orbit at roughly 35,700 kilometers. Apophis will move beneath that ring, slipping between Earth and the high technological shell we have placed around it, at about 1/10th of the distance to the Moon. In ordinary speech, we might call that a near miss. On the scale of the solar system, it feels more like a brush along the edge of Earth's presence. Its rarity is what gives the encounter its weight. Small bodies, perhaps the size of a car or a bus, pass between Earth and the Moon often. We detect some each month, while others are noticed only after they have already moved on. But something comparable to Apophis, spanning 340 m or more, and coming this close, belongs to a far less common class of event. Statistically, an object of this size passes this near to Earth about once every 7,500 years. That is not simply beyond a human lifespan. It reaches across the scale of recorded civilization. The last time a body this large came so near, there were no cities, no writing, no telescopes, and no scientific framework for recognizing what was overhead. This time, we will not merely witness the passage, we will understand enough to be unsettled by it. It is also important to imagine the view correctly. The word asteroid may summon thoughts of fire and impact, but Apophis will not enter the atmosphere. There will be no burning trail, no blazing tail, no explosion across the sky. What observers should see is steadier and perhaps stranger, a star-like point that seems to have slipped free from the celestial pattern, gliding across the constellations. Over roughly an hour, its position will change noticeably against the background of stars. Look away, then return, and it may have shifted. The comparison to the International Space Station is useful, but only up to a point. This will not be a spacecraft in low orbit, about the size of a football field. It will be a mountain of rock, tens of thousands of kilometers away, moving with a brightness and purpose that could make the night feel briefly rearranged. That brightness carries its own message. For an object at that distance to be visible to the naked eye, it must be both large and close. A span of 340 m is longer than 3 American football fields placed end to end. If stood upright, it would rise higher than the Eiffel Tower and taller than the Empire State Building. This is not a small stone wandering harmlessly through the dark. On a different path, in another version of events, an object like this could represent a civilization-level threat. That possibility is part of why Apophis once caused so much alarm, and part of why the relief that it will miss Earth does not end the story. Knowing it will pass by is comforting. Understanding what the passage will do to it is another matter. So, the situation has an almost dreamlike tension. 4 years from now, humanity has an appointment with a skyscraper-sized rubble pile, and the time and place of that appointment can be predicted to the kilometer and the minute. Yet the visitor remains poorly understood in the ways that matter most for its physical nature. We know the route, but not the temperament of the traveler. We can point to where it will be, while still asking what kind of body is actually arriving. Solid, fractured, loosely bound, or something more complicated. That gap between orbital certainty and physical mystery is why scientists are not content to treat the 13th of April 2029 as only a spectacle. It may become a rare natural experiment, with Earth's gravity acting as the apparatus and the so-called god of chaos serving as the specimen. Even the name seems to lean into the unease. The object is called Apophis. In ancient Egyptian stories, Apophis, sometimes written as a pep, was the great serpent of darkness and chaos, the presence that waited in the underworld each night to devour the sun and bring the world to an end. Each morning the sun escaped and rose again. Each night the struggle resumed. That is the mythic name attached to this asteroid. And it gives the approaching flyby a symbolic shadow it does not scientifically need. Perhaps that is why the story lingers. A precisely tracked rock is coming close. It will not hit us. And still, it asks a question that feels older than astronomy. What happens when chaos passes near enough for everyone to see? And, with a coincidence that feels almost too theatrical for fiction, the date of its closest approach, the night when the serpent seems to glide nearest to Earth, lands on Friday the 13th. But before anything else, the most important point needs to be placed calmly in the open. Apophis is not on course to strike our planet. This is not a slow walk towards some hidden impact scenario, because no such scenario exists. Its future path has been measured with extraordinary precision. Among the best-known trajectories for any object moving through the solar system, the specialists whose work is to calculate these hazards have checked the orbit, refined it, and checked it again, and a collision with Earth has been ruled out for at least the next 100 years. The mystery is not where Apophis is going. On that point, the answer is stable enough that you can rest tonight. So the more interesting question is quieter, and perhaps more revealing. If the orbit is safe, why are planetary scientists watching the 13th of April 2029 with such unusual attention? Why does this flyby carry a sense of suspense that has almost nothing to do with impact and almost everything to do with the asteroid itself? The reason is simple and also unsettling. We can say where Apophis will be on that Friday night to within a kilometer, yet we know remarkably little about what kind of object it truly is. In a sense, we know its location far better than we know its nature. As observing tools have improved and models have become more refined, the portrait has not become more ordinary, it has become stranger. Its shape is unusual, its rotation is unusual. And the more closely researchers examine it, the less it resembles the straightforward solid boulder that people may once have imagined. Something about Apophis does not fit neatly. Those who study it can see that tension. Beneath the spectacle of the 2029 passage, something physical will be happening. As Apophis sweeps by Earth, our planet's gravity will take hold of it in a very real way, not as metaphor and not as a gentle influence. The same force that keeps you seated and lifts the ocean tides will act on a 340m asteroid, pulling, flexing, and twisting it in a manner it may not have experienced for millions of years. Without setting out to do so, we are about to conduct an experiment on the god of chaos. Earth becomes the hand, Apophis becomes the object being grasped. And at the heart of this story is a fact that cannot be made more comfortable. No one, not the modelers, not the mission planners, not the scientists who have followed this body for 20 years, can say with certainty how it will react. This is where the drama cannot be removed by one clean calculation. The response of Apophis in 2029 depends on the one essential property that distant observations cannot directly reveal: the structure and strength of its interior. Telescopes can be aimed at it from across Earth. Radar can be sent toward it for years. But none of that lets us simply look inside a solid object when it is hundreds of millions of kilometers away. Its interior remains silent. The answer is not lying openly in an equation, waiting for someone to finish the algebra. It is sealed within the body itself, and the only thing that can test it is force, real force, acting on the real asteroid while we watch. In a modern scientific age, filled with simulations and remote measurements, that is almost an old-fashioned kind of uncertainty. We may not merely infer the answer, we may have to disturb the object and observe what follows. That is the source of the unease. It is not a fear of collision. It is the suspense of a single, natural experiment, performed on a famous but still poorly understood body, in view of the world, with no rehearsal and no second attempt. There will be one pass, one night, and whatever Apophis does when Earth's gravity grips it, it will happen only once. Either our instruments will be ready enough to interpret it, or a rare chance will slip past us. That is the path we are taking tonight. We will examine what this object appears to be, and how it changed in human understanding from a number that genuinely unsettled astronomers into a rock whose course can now be predicted. We will consider its shape, which seems as though it should not look quite the way it does. We will follow its tumbling motion through space, a motion that does not behave like the simplest picture of a rigid stone, and one that many people online have noticed and are debating now. Step by step, we will look at what Earth's gravity is expected to do during the encounter, along with the possible outcomes from uneventful to genuinely astonishing. We will also consider the machines and observing systems that will be watching when the moment arrives. Yet every part of the story returns to one central question, and it is worth keeping that question close for the next 2 hours. What is actually inside Apophis? Not the visible surface, not the orbit we can calculate. The hidden interior, the region no telescope has ever seen and no spacecraft has ever touched. That answer may decide everything else. It determines what happens in 2029, and the strangest possibility is that we may not learn it until the experiment is already in motion. So, we begin with the rock itself, and with a night, years ago now, when Apophis first appeared on our screens, carrying a number that made very serious people go quiet. Part 2. The asteroid that once had a number beside Earth's name. The story of Apophis begins on a desert mountaintop in Arizona on the 19th of June 2004. That date is more important than it first appears, and we will return to its significance shortly. At Kitt Peak National Observatory, 3 astronomers, Roy Tucker, David Tholen, and Fabrizio Bernardi, noticed a dim point in their data. It was a new near-Earth asteroid, one among the many found each year. At first, nothing about that faint mark suggested it would become the most widely known asteroid on the planet. It was simply logged as another moving point of light and sent onward for follow-up observations, as such discoveries usually are. The name came afterward, and its origin is more playful than one might expect from an object that would briefly alarm the world. Once the orbit of a newly discovered asteroid is confirmed, its discoverers are allowed to name it. The team who found this one enjoyed a science fiction television series whose main villain was a parasitic alien pretending to be a god called Apophis after the ancient Egyptian deity. So, the name began as a reference to a television antagonist. Only later did people notice how eerily well the older meaning seemed to match. In Egyptian myth, the original Apis was not just another god. In Egyptian myth, the serpent was not merely a monster in the dark. It was the image of disorder itself, the force of unraveling, waiting below the world each night to swallow the sun and undo creation before dawn could return. So, when astronomers gave the name Apophis to a near-Earth asteroid, there was a strange poetry to it. At first, the name carried a hint of dark humor. Then, for a short time, mathematics made the joke feel uncomfortably close to prophecy. The fear did not come from myth alone. It came from a number, 2.7%. To see why that figure mattered so much, we need to return to the Torino scale, the simple public scale used to describe the danger posed by asteroids. It begins at 0, where there is no meaningful concern, and rises to 10, where a collision is certain and the consequences would be global. Most objects that receive any rating at all sit at 0 or 1, and as astronomers gather more observations, they usually drift back down to 0 without drama. In other words, the system is built so that a high score is unusual. Falling away from danger is the expected pattern. Apophis did not follow that quiet path. It rose to level 4, a category meant for a close approach that deserves attention from astronomers, with a genuine, though still limited, chance of regional devastation. No asteroid had ever reached that rating before. None has done so since. For several days, near the end of 2004, the most threatening object ever placed in humanity's catalogue carried the name of Chaos and had a date attached to it, the 13th of April, 2029. It is not hard to understand why that combination stayed in public memory. A mythic name, a precise date, and a measurable risk can make even the calm language of astronomy feel suddenly intimate. And there is one small coincidence worth noticing. The day this story is being told, the 19th of June, is exactly 22 years after Apophis was discovered. That does not imply any hidden cosmic message. It is simply the calendar aligning in a curious way. Still, it reminds us that this asteroid has not been a passing headline. It has remained in the records for more than 2 decades. Observed again and again, its orbit sharpened with remarkable accuracy, while the physical rock itself has remained, in many ways, unfamiliar. After its discovery, the story accelerated quickly. During late 2004, new measurements began feeding into orbital calculations, and the people studying the trajectory saw something rare and deeply unwelcome. The projected route years ahead was drawing nearer to Earth, while the uncertainty in the early data remained broad enough that a possible impact could no longer be treated as a distant abstraction. By late December, calculations suggested that Apophis had about a 2.7% chance of striking Earth during the 2029 encounter. That number deserves a moment of stillness. Less than 3 in 100 may sound small in ordinary life, But this was not about rain on a holiday or the outcome of a game. It was the estimated chance that a 300-meter asteroid could collide with the planet beneath our feet. Put another way, it was roughly a 1 × 37 possibility that an object capable of flattening a metropolitan area or raising a tsunami across an ocean would arrive on a date already visible on the calendar. That is the kind of probability that changes tone when the consequences become enormous. The Torino scale exists precisely to give such risks a common language, and Apophis reaching level 4 made it unique. A 4 had never been assigned to an asteroid before, and it has never been assigned again. For that brief interval, Apophis held the unsettling distinction of being the most dangerous space rock we had ever identified. Yet the danger did not end in a simple yes or no. Even when later observations eliminated the possibility of a direct impact in 2029, a more delicate problem remained. During that close pass, Apophis might have crossed an extremely small region of space known as a keyhole. In orbital mechanics, a keyhole is a narrow gravitational doorway, a patch no more than about 0.8 of a kilometer wide. If an asteroid passes through exactly that region, Earth's gravity can alter its path by just the right amount, placing it onto a future orbit that leads to a later collision. So, the question changed. It was no longer only whether Apophis would miss Earth in 2029. It became whether the miss would be clean, or whether the asteroid would slip through the one tiny zone that could bring it back in 2036 or 2068. For a few years, that possibility kept Apophis on watch lists. There is something quietly unnerving about the idea that an object can pass safely by, and yet cross an invisible point that reshapes its future into danger. But this is also where the careful machinery of planetary defense did what it is designed to do. Astronomers continued observing. They collected more measurements, improved the orbit, and reduced the uncertainty. Then, in March of 2021, using the enormous radar dish at the Goldstone complex in California, together with other observatories, they determined the path with enough precision to make a rare and comforting declaration. Apophis was cleared. The radar observations ruled out any impact from Apophis for at least the next 100 years. The chance of a strike during the 2036 encounter fell to about 1 in a billion. For 2068, it dropped to roughly 1 in a million. For now, the serpent has no route to Earth. The keyhole idea is worth making more tangible, because it is one of the stranger and more counterintuitive notions in orbital mechanics. Imagine standing at one edge of a golf course. Far away, across the green, there is a wall with a single open window in a distant clubhouse. Beyond that window, farther still, is the hole. To make the shot, the ball must pass through that exact window first. If it misses the opening by even a small amount, it continues harmlessly past the clubhouse, and the final hole is never threatened. A gravitational keyhole works in a similar way. It is a tiny region of space, less than a kilometer across, and only if Apophis had passed through that exact patch in 2029 would Earth's gravity have bent its trajectory into the precise new orbit needed for a later impact. Everywhere else around that patch, and there is an immense amount of everywhere else, the asteroid simply moves on, and the future remains safe. For several years, the central challenge was whether we could measure the path finely enough to know if Apophis would thread that invisible window. Eventually, we could, but to reach that confidence, astronomers had to include a force so faint that many people have never encountered its name, yet important enough to matter here in more than one way. It is called the Yarkovsky effect. The principle is subtle, and it begins with a simple idea. Sunlight does more than illuminate an asteroid. On the side facing the sun, the surface warms. As the body turns, that heated region is carried onward, and the stored energy is later released back into space from a slightly shifted direction. That departing infrared radiation gives the asteroid an almost unimaginably small recoil, a kind of silent exhaust. Over a single day it is tiny, but across years and decades, That subtle force can move an orbit enough to matter. For Apophis, measuring the Apophis push was a crucial part of deciding whether it would pass through the gravitational keyhole. Yet the same measurement carried another message. The strength of the Apophis push depends on the way an object stores and sheds heat, and that depends on its surface and interior. So the data that helped remove Apophis from the impact list also suggested that it may be loose, porous, and low density, rather than a single, solid rock. In a quiet way, reassurance and mystery arrived together. That matters, because the story of Apophis is often remembered for the fear, but the deeper lesson is about evidence. The original alarm played out during the Christmas season of 2004, as the calculated probability rose in the last days of December, and astronomers across the world exchanged urgent updates. When the danger was ruled out, that conclusion was made public. The rising odds, the concern over the keyhole, the long years of careful tracking, and the radar observations that finally closed the case, all appeared in the open scientific record and in the press. This is worth holding on to, because later claims that the truth about Apophis is being concealed run directly against the documented history of the object. Confidence here does not come from loyalty to an institution, it comes from measurement. Radar lets us send radio waves toward an asteroid, catch the returning echo, and determine not only its position, but its motion toward or away from Earth, with precision down to a fraction of a millimeter per second. Add that to more than 20 years of optical observations reaching back to that night at Kitt Peak, and the result is an orbit known with extraordinary clarity. The location of Apophis in 2029 is better constrained than that of almost anything else in its class. In other words, the path is not the uncertain path. The strange part is what that certainty reveals by contrast. We know the orbit beautifully, but the object itself remains unfamiliar. There is something almost uneven about that. We can say, to within kilometers, where a 340 m body will be 4 years from now, on a particular evening, after it has traveled hundreds of millions of km around the Sunday. But ask what it is made from, how strong it is, or what lies beneath the surface, and the answer becomes much less satisfying. Mostly, we do not know. We have followed the dance with remarkable precision. The dancer has barely shown its face. At first, that gap feels surprising, but it makes sense once we remember how asteroid science works. An orbit gives itself away slowly, one measured position after another, until the path becomes unavoidable. An interior does not announce itself. It remains dark, quiet, and distant, hundreds of millions of kilometers away, offering little unless a spacecraft visits or some outside event disturbs it. Until very recently, nothing was expected to disturb Apophis, and so we are left with a useful frustration. The very precision of the orbit makes the ignorance about the interior stand out. Because we know where Apophis will be, spacecraft can be aimed, observations can be timed to the second, and the 2029 encounter can become one of the most anticipated natural experiments in planetary science. What no one can forecast is what that experiment will show about the hidden part of Apophis. The first strong hint that the inside might not be simple did not come from a spacecraft at all. It came from the stubborn fact that, when radar finally gave us a usable sense of its form, the asteroid looked like something it almost should not have been. In part 3, we come to the shape that should not be there. The 2021 radar data gave astronomers more than a refined trajectory. It offered a rough, grainy, difficult image of Apophis itself. The first real outline of a body that had previously been little more than a moving point of light. What appeared was not the familiar mental picture of an asteroid as a rounded potato or a single battered boulder. It was longer, drawn out along one axis, and seemingly pinched at the center. Two broader lobes appeared to meet at a narrower waist. Researchers reached for simple comparisons because the shape almost demanded them. A peanut, a dumbbell, two rocks touching. Those images may sound casual, but they point towards something important. Shape can be a record of history, and in this case, it also raises questions about structure. In asteroid science, such a form has a specific name, a contact binary. The phrase means almost exactly what it suggests. Rather than one cleanly unified object, there may be two bodies involved. Long ago, they could have drifted together, made contact, and remained there, held by their own faint mutual gravity. They would not need to be melted together or welded into a single solid mass. They could simply rest against each other at a seam, like two boulders that met gently and never separated. That possibility changes the way we imagine the asteroid. It becomes less like a carved stone and more like an arrangement held together by delicately balanced forces. How could such a thing form? The possible routes are few, but each one hints at how loosely assembled many small solar system bodies may be. In one scenario, two separate asteroids traveling on similar paths approached each other so slowly, perhaps only a few centimeters, walking pace or less, that they did not smash apart. They touched and remained together. In another scenario, a single rubble pile was gradually spun up by sunlight, through a related effect to the Apophis effect mentioned earlier, until it stretched, divided, and then partly settled back into a two-lobed form. Different histories, but the message is similar. Objects like this are not necessarily solid sculptures cut from stone. They may be fragile, irregular gatherings whose strength, shape, and future behavior depend on how their pieces are arranged inside. And that is why the shape of Apophis is more than a silhouette. It is a question waiting for the 2029 encounter to ask more clearly. These objects are not solid monuments in the way a mountain might appear solid from far away. They are more like collections, assembled fragment by fragment, keeping their present outlines with only the gentlest kind of cohesion. Once that pattern becomes familiar, it begins to appear again and again wherever spacecraft have gone to look closely. The small asteroid visited by Hayabusa, for example, has that same swollen, uneven character, like a peanut or a sea otter, suggesting two portions settled against one another rather than one cleanly formed body. Rosetta, when it reached Comet 67P, revealed something similar in a more dramatic form. Not one simple, dirty snowball, but two large lows connected by a narrow neck, an outline that called to mind a rubber duck. That thin middle region became one of the mission's most scrutinized details, because stress fractures could be seen running through it. Farther out, near the outer edge of the solar system, New Horizon passed the distant object nicknamed Arakoth and returned images of an almost ideal contact binary, two rounded lows pressed together like a quiet snowman drifting in the dark. Taken together, these encounters have given us a small but powerful gallery of worlds built around a join, a waist, a seam, a neck, the place where two bodies became one without ever fully losing their separate identities. That is why Apophis should not be treated as a strange exception. It belongs to a class of objects we are beginning to recognize, and that makes the 2029 prediction more meaningful rather than more speculative. We are not facing a never-before-imagined shape. We are studying a known kind of body with a known kind of fragile region, and asking how it may respond to a known kind of gravitational strain. The radar views of Apophis are rough, especially beside the close portraits of Itokawa or Arioth. They look less like photographs than blurred shadows. Yet even through that graininess, the essential architecture is visible. Two lows, a constricted middle, a seam. And this is not some rare oddity hidden at the margins of the asteroid population. Among near-Earth asteroids larger than about 200 meters, close to 15% seem to share this two-lobed, billowed form. In other words, Apophis is part of a real and recognized family, bodies assembled from smaller pieces and now moving through space as loosely connected pairs. Still, common does not mean unimportant. A shape can be widespread and still carry a warning, because shape tells us where stress may concentrate and where a body may be easiest to disturb. The quiet question beneath all of this is simple. If the outline marks the weakness, what will happen when that weakness is pulled? At this point, it is natural to wonder how anyone can know the form of a rock only a few hundred meters across when it lies tens of millions of kilometers away. To an ordinary telescope, such an object would be no more than a point of light, far too small and too distant to reveal its body directly. The answer is one of astronomy's most graceful methods, radar. A huge dish, such as the one at Goldstone, is aimed toward the asteroid, and a strong pulse of radio waves is sent across the gulf between worlds. Those waves strike the surface and return, extremely faint, to be collected and measured. The method works because the asteroid is not all at one distance. Its nearer side sends back an echo just slightly sooner than its farther side, by a tiny fraction of a second. At the same time, because the asteroid rotates, one edge is turning toward us while the other is moving away, shifting the frequency of the returning signal in the familiar manner of a siren whose pitch changes as it passes. By combining the arrival times and frequency shifts from millions of echoes, scientists can infer a three-dimensional form from reflected radio waves alone. It is almost as if we are touching the asteroid with invisible fingertips, feeling its contours across 17 million kilometers of empty space. What those radio fingers outlined was the same pinched, two-lobed body, tightened at the center by a neck. That image matters because it is not merely a silhouette. It is a clue to structure and perhaps to vulnerability. A distant speck becomes a physical object, and the question becomes less about where it is and more about how it is held together. That is why the neck keeps returning to the center of the story. It is not a decorative feature or a minor detail in the outline. It is the seam of the entire body. In a two-lobed object, the neck is where the lobes meet, where the body narrows and where the two parts appear to be joined. Wherever there is a join, there may also be a weakness. The idea is familiar from ordinary experience. When something made from two attached pieces fails, it usually does not split through the strongest middle of either piece. It gives way where the pieces meet. The neck of a puff is that meeting point. It is the kind of region that becomes especially important when forces begin to tug the two halves in different directions. This is also the feature that has stirred so much attention online. A theory has been moving through social media in recent days, built around this very shape, essentially arguing that the asteroid looks like two rocks connected by a thin neck and that this should make us uneasy. It is worth treating that reaction carefully. The instinct is not baseless. People sharing that thread are looking at an actual radar-derived form, noticing a genuine structural feature, and drawing a conclusion that has a reasonable core. A bilabid asteroid with a narrow central connection really is more fragile in principle than a single compact boulder. Some of the drama attached to the argument goes beyond what the evidence can support, and that boundary matters. But the basic observation that the shape points to a weak place is not wrong. Something true has been noticed, even if the interpretation may need restraint. So keep the picture steady in your mind. An elongated object, a few football fields across, made of two lows resting together and held at the most delicate part by a narrow neck. That is the body we are discussing. And the thread to carry forward is this. In 2029, Earth's gravity is expected to pull most strongly on that same seam, the weakest line running through the asteroid. The outline is not just a curiosity on a radar model. It is a kind of map, showing where the coming gravitational test may press hardest. In a calm sky, that might sound abstract, but in the geometry of a close pass, the form of the object becomes part of the event itself. Yet the shape is only one half of the strangers. When scientists looked beyond the outline of Apophis and considered how heavy it is for its size, along with the unusual way it tumbles through space, the picture became even less like a simple rock. It began to suggest something more fragile, a pile of rubble wearing the mask of a rock. Part 4 begins with a question that sounds almost too basic, yet it is among the most important questions one can ask about an asteroid. How heavy is it for its size? Not simply how wide it is, and not only its total mass, but how densely its material is packed. Density tells us how much matter occupies a given volume, and from that, it offers clues about composition and about the way the object holds together. For a body that may be assembled from pieces, this is more than a measurement. It is a way of asking whether we are looking at a compact stone or something far looser. When scientists calculated the density of Ape, the result was low. That number does not merely describe weight, it quietly changes the character of the entire object, suggesting that what appears from afar to be a rock may, in structure, be something much less solid. The density figure is the first clue, and it is an oddly quiet one, about 1.75 grams per cm. A solid stony rock on an Earth mountain would usually sit nearer to 3 g per cm, sometimes higher. So Apus appears far too light for its apparent size. That mismatch matters because mass is not easy to hide. If this asteroid were one continuous block of stone, a single compact boulder moving through space, it should be much heavier than the measurements suggest. The simpler explanation is stranger, but more physical. A large part of Apus is not material at all. It must contain gaps, cavities, loose contacts, and empty pockets threaded through its interior. Estimates place its porosity, meaning the share of its volume that is simply open space, at roughly 40%. Almost half of it, by volume, may be absence. In that sense, the object is not best imagined as a mountain. It is better understood as a fragile aggregate, a body that only looks solid from far away. This is the kind of asteroid scientists describe as a rubble pile, and the phrase is more literal than it sounds. Instead of one monolithic rock, picture a slow-moving collection of dust, sand, gravel, and boulders, with pieces ranging from tiny grains to blocks as large as houses. They are not welded together, not cemented into a rigid body, and not bound by strong internal bonds. What keeps them gathered is mostly their own very weak mutual gravity. A rubble pile is therefore closer to a mound of sand, preserving a shape under the lightest possible hold, than to a stone you could pick up and strike. In principle, something like a hand could push into such a surface. A sufficiently strong outside pull could shift the arrangement, because the entire structure is held together by forces that are delicate rather than firm. That image may sound speculative, but it is not being formed in isolation. Spacecraft have visited similar small worlds and found this kind of looseness directly. When Japan's Hayabusa spacecraft reached the small asteroid Takawa, the scene matched the rubble pile idea. Boulders and gravel assembled with little sign of a solid central core, so weakly gathered that the body seemed only barely unified. Apus resembles Itokawa in the ways that can be measured, including its probable stony composition, rich in minerals such as olivine and pyroxene, and related to a common class of meteorites that reach Earth. Bennu offered another vivid example. During the OSIRIS-REx mission, the spacecraft touched the asteroid to collect a sample and sank into the surface as though it had pressed into a ball pit, nearly burying itself. The scientist leading that mission later explained that a person stepping onto Bennu might sink as if into plastic balls, and that without firing its thrusters to retreat, the spacecraft could have continued downward. Such details change the mental picture. These are not the hard, clean asteroids of imagination. They are airborne rubble fields, temporarily gathered into shape. So where does a rubble pile begin? The leading explanation is simple and almost brutal. In the distant past, a larger parent body, perhaps a more coherent asteroid, was struck and broken apart in a collision with another object. That impact scattered thousands or millions of fragments, but the pieces did not all escape forever. Over thousands of years, The weak gravity among the debris drew some of it back together. What formed again was not the original solid object, but a loose heap, a gravitational clump made from broken parts, full of spaces and imperfect contacts, more like something poured into place than something carved from a single mass. In this view, Apophis is the reassembled remnant of an earlier body that was shattered long ago. Its 40% emptiness may be read as a kind of structural memory. The unclosed spaces between fragments that never fused back into stone, and the binding force is astonishingly slight. This is not the chemical bonding that gives a boulder its strength. It is mostly gravity, with a faint surface stickiness between grains, the subtle attraction that can make flour clump together or dust cling where it lands. Across a body the size of a puff, those tiny effects add up to something measurable, but only barely. That is why the 2029 encounter remains so compelling. A body held together by a whisper will pass through the gravitational reach of an entire planet. If Apophis were a solid rock, the question would hardly arise. It would pass by and remain essentially itself. But for a rubble pile, the outcome is more open, and that uncertainty is exactly where the science becomes interesting. Its strange tumbling motion fits this fragile interior picture especially well. To see why, it helps to ask why a tumble would last at all. Over long stretches of time, most objects are expected to drift toward a simpler spin. As a body wobbles, tiny internal flexing, rubbing, and friction should slowly drain energy from that motion until only a cleaner rotation remains, much as a spinning top either steadies for a time or finally collapses. If an asteroid is still tumbling, then one of two broad possibilities may be involved. Something may have disturbed it relatively recently, or its internal structure may be arranged in such a way that the wobble has not died away even over the age of the solar system. Either possibility points inward. The tumble is not just a motion seen from outside, it can act like a record of what the interior is capable of doing. It is a slow clock, keeping time through the body of Apophis, and learning to read that clock is one of the few ways to ask what lies beneath the surface. This is the idea that online arguments sometimes circle around, even if the exact numbers being traded in those threads are not ones to trust too strongly. The distribution of mass inside a body, what physicists call its moment of inertia, controls how that body tumbles. Shift mass from one region to another, make one lobe denser, leave a hollowed area elsewhere, or pack part of the interior more tightly, and the rotational behavior changes. A measured tumble that fails to match the simplest model is therefore not a paradox, and it does not require anything outside ordinary physics. It may simply be the interior expressing itself through motion. For Apophis, that motion is the only voice the hidden structure has, and it may have been speaking all along, waiting for the right instruments and the right interpretation. Then there is the spin itself, the part that feels most unsettling in a quiet way. Many objects in space, when left alone, tend toward a smooth, stable rotation around a single axis, like a well-thrown football spiraling cleanly, or a planet turning around its pole. Apophis does not behave that neatly. It tumbles in what scientists call a non-principal axis rotation, meaning it is effectively rotating around more than one axis at once. The result is a combined rolling and wobbling motion that does not settle into a simple, repeating pattern. The strongest rhythm in that tumble lasts about 30½ hours, while a second, slower wobble is layered on top of it at something closer to 263 hours. Imagine a football thrown without skill, flipping end over end while also drifting sideways, never finding a stable spiral. In that restless motion, the so-called God of Chaos moves through space not as a clean stone, but as a loose, haunted collection of fragments, turning in a way that may be telling us how delicately it is held together. It is not simply rotating like a clean, balanced top. It is tumbling, And that awkward motion is the detail the viral online argument has latched onto. The claim deserves a careful look, because beneath the exaggeration there may be a real physical clue. In broad terms, the thread argues that a simple, rigid, uniform body should have a predictable relationship between its faster spin and its slower wobble. According to that argument, the expected ratio is one value, while the reported ratio is quite different, supposedly off by about a factor of 2. From there, the thread makes its dramatic leap. It suggests that something inside Apophis must be flexing, that the object is not acting like a solid block because, in some sense, it is not a solid block at all. It may be shifting, yielding, and rearranging internally as it moves, but we need to slow down here. The exact figures being shared in that thread, the specific numbers and ratios, cannot be verified from what is presented, so they should be treated as examples rather than established measurements. They have the quality of numbers that may have grown more precise each time they were repeated. Still, the broader idea points toward legitimate science. A tumbling object's motion depends very sensitively on how its mass is arranged inside. A smooth, uniform solid will tumble in one pattern. A body with dense pockets, loose zones, and uneven structure will behave differently. So, if a real asteroid fails to match the motion expected from an idealized, uniform rock, that does not imply anything mysterious. It is more like a signature. The unseen interior is writing itself into the spin. A strange wobble is exactly the kind of thing one might expect from a lumpy, heterogeneous rubble pile whose mass is distributed unevenly beneath the surface. And this is why the motion matters. The spin becomes a kind of window, perhaps one of the only windows available, into the part of Apophis that telescopes cannot directly reveal. We cannot slice a puff open and inspect its hidden structure, but we can watch how it rolls, hesitates, and wobbles through space, quietly, second by second. Its movement may be reporting on the arrangement of mass buried inside. That brings the whole story back to one central idea. If the tumble of Apophis is being shaped by its concealed interior, then the most revealing experiment would be to push the asteroid and watch how the tumble responds. Measure the rotation before the shove, apply a force, then measure it again afterward. The difference could speak about the interior in a way that images alone cannot. And this is not merely an imagined experiment. In 2029, something very close to that will occur. The push will not come from a spacecraft or from us. It will come from Earth itself. So the next question becomes calm but profound. What happens when a planet reaches out and squeezes a ghost? Part 5. When a planet squeezes a ghost. To understand what Earth will do to Apophis, we first have to name a force you already know from experience, even if you rarely think of it this way. It is the force that lifts the ocean into tides and lets it fall back again. It is also the same effect that has gradually kept the moon turned so that one face remains toward us. We call it the tidal force, though it is not really a new force, separate from gravity. It is gravity acting unevenly across an extended body. Because gravity weakens with distance, the side of an object closer to Earth feels a slightly stronger pull than the side farther away. For a large object, that difference matters. It creates a stretch from one end to the other, a gradient in the pull. In the oceans, that gradient raises tides. For a loosely held rubble pile, passing 31,000 kilometers overhead, it becomes a far more delicate and interesting disturbance. Imagine the approach of Apophis. It follows its precisely known path toward Earth and enters a region where our planet's gravity is not only strong, but changing rapidly over distance. The face turned toward Earth is tugged harder than the far side, so the body is drawn out along the Earth-pointing line. Meanwhile, because the asteroid is tumbling, different regions rotate through that line of greatest stress again and again during the hours around closest approach. Earth does not deliver one simple pull to a puff and then let it go. It tugs, twists, stretches, and relaxes the body as it passes, rather like hands working a lump of dough. For a rubble pile, held together by the faintest grip, this may be the most intense encounter it has experienced in a very, very long time. That image matters because it frames the event not as a collision, but as a gravitational test. The asteroid is being asked, gently but firmly, how strongly it holds itself together. There is, however, an important boundary in space that tells us whether tidal squeezing should rip a body apart or merely disturb it. This boundary is worth pausing over, because it is both the best reason not to panic and the reason the scientific question remains open. It is called the Rho limit. The Roche limit is the distance from a planet within which tidal stretching becomes powerful enough to pull apart a body held together only by its own gravity. Inside that line, a strengthless rubble pile cannot remain intact. Outside it, gravity can still hold the body together. For Earth, and for a low-density body like Apophis, that limit lies at about 18,000 kilometers from the planet's center. Now compare that with the key distance for the 2029 passage. Apophis will come no closer than roughly 38,000 kilometers from the center of the Earth. That is well beyond the Rho limit. It is not skimming the boundary where pure self-gravity would fail. This is why the models do not predict that Apophis will simply fall apart. It will move through a region where it is stressed and disturbed, not a region where it should be dismantled outright. Yet the suspense does not disappear, because the rush limit is a clean threshold for total disruption of a body held together only by gravity, and real objects are not so clean. Real rubble piles may have a little extra cohesion, a faint stickiness between grains that helps them resist deformation. At the same time, they may also contain weak zones, like our neck, where local strength is much lower than the average. So the rash limit tells us that the body should not be torn to pieces. It does not tell us that nothing will change. The tidal calculation can reveal that stress is coming, but it cannot neatly announce what the asteroid will do with that stress. It cannot say in advance whether one lobe will slide, whether loose material will break into an avalanche, whether the rotation will be altered abruptly or only slightly, or whether a weaker neck between pieces will simply yield by a small amount. Those possibilities belong to the uncertain zone between no visible effect and outright disruption. And in that in-between region, the hidden interior of Apophis becomes the judge. This is why the science turns from a clean equation into something closer to a carefully controlled reconstruction. Researchers cannot treat the asteroid as one simple solid and expect the answer to be complete. Instead, they build a virtual body from many interacting parts. In the most detailed simulations, Apophis is assembled from thousands of individual particles. Some studies use around 4,600, with each particle representing a piece of the rubble pile. Then the model is allowed to pass through Earth's gravity, with every particle pushing, pulling, touching, and colliding with its neighbors throughout the flyby. The experiment is repeated again and again, because the starting assumptions matter. One run may give the two lobes the same density. Another may make the head up to 70% denser than the body. Other trials raise or lower the cohesion by small amounts. Each version becomes a different possible Apophis, and each version reacts in its own way. The result is not one neat prediction, but a family of futures. That spread is the heart of the suspense. The asteroid may be about to tell us something that no telescope can read from the outside alone. To feel why this matters, we have to slow the encounter down. It is not a single flash of action, but a gradual event unfolding across much of a day. Long before closest approach, Earth's gravity is still weak and fairly uniform across the asteroid. Apophis continues its long tumbling motion, while the spacecraft traveling with it gather the quiet reference data, the spin state, the shape, the surface details, and the precise condition before anything changes. This is the baseline, the still moment before the experiment begins. As the asteroid moves inward, the pull on the side facing Earth begins to differ more and more from the pull on the far side. At first, the change is subtle. Then, as distance falls, the tidal stretching grows more quickly. A body that may have spent millions of years without such a close planetary disturbance begins to feel an uneven force across itself. The question is not simply whether Earth pulls on it, but whether that pull is enough to rearrange what was already fragile. Then comes closest approach, that evening over the Atlantic, when the stress reaches its maximum. For a few minutes, the gravitational grip is strongest, and the stretching across the asteroid is at its peak. If anything is going to move, this is the crucial window. If the neck is going to release some compression and allow a lobe to roll, it is here. If loose slopes are going to fail, the first avalanches would begin here. If the spin is going to be pulled toward a new rate or direction, this is the moment of the wrench. Yet the peak does not last. Apophis is moving rapidly, and it does not remain in Earth's strongest tide. Within hours, it is already departing, the stress dropping away almost as quickly as it rose. Afterward, the asteroid is left to settle into whatever condition the encounter has produced. A rare and possibly transformative event, one we have a front-row chance to witness, is essentially compressed into a single afternoon. The key measurement, the one that turns this natural flyby into a readable experiment, is rotation. Before the encounter, scientists measure exactly how Apophis tumbles, its rate, its axis, and its wobble. Afterward, they measure those same properties again. The comparison becomes the asteroid's reply. A very small change would suggest an interior that is comparatively strong, well-connected, and resistant to deformation, behaving more like a coherent object than a loosely assembled heap. A large change would point in the opposite direction. If the rate nearly doubles, or nearly halves, and if the rotation axis swings toward a new orientation, then the interior is likely weak, loose, and easily shifted. A genuine rubble pile that Earth's tide could seize and reshape. In that sense, spin becomes the language of the unseen interior. The flyby gives us the rare chance to hear it clearly, because the disturbance is not random background noise. It is a known event with a before and an after. Imagine the two broad endings to understand what is at stake. In the quieter outcome, the spacecraft watch Apophis pass through the encounter with only modest change. Its rotation adjusts a little, perhaps a few small landslides disturb the surface, and the asteroid emerges looking much like it did before. Even that would be important, because it would imply that Apophis is stronger than its low density might have led us to expect. A calm result would still be a meaningful result. In the more dramatic outcome, the tumble changes visibly over the hours. Fresh material may slide into view, exposing brighter ground beneath the older weathered skin. The two lobes could shift subtly against each other at the neck, leaving instruments to record a body measurably altered by its passage near Earth. Such a response would suggest that objects like this are more delicate and more dynamically responsive than they first appear. Either path is scientifically valuable. Either one would change part of the story we tell about small asteroids. But the choice between them belongs to Apophis, and the answer must come during the brief afternoon when Earth tests it. Within that larger range of outcomes, the surface response is especially compelling, because it is the part observers have the best chance to see directly. When the rotation changes and tidal stress moves through the body, the balance of forces holding loose surface material in place also changes. On a world with such weak gravity, grains, pebbles, and boulders are only lightly anchored. A small disturbance may be enough to start motion. A slow creep down a slope, a shifting patch of rubble, or an avalanche moving across the surface in low gravity. Scientists call this resurfacing, and the word sounds simple for something that could be profoundly revealing. The reason lies just beneath the exterior. Over millions of years, an asteroid's outermost layer is altered by solar radiation and micrometeorites, through a process called space weathering that darkens and reddens the surface and changes its appearance. Below that, aged skin is cleaner, less altered material. A closer look at what the asteroid is made of beneath its exposed face. If the 2029 encounter causes landslides that peel away the weathered layer and uncover fresh material below, then we may see the unweathered face of a near-Earth asteroid for the first time. It would not be revealed by a drill or by returning a sample, but by the tidal hand of our own planet. And this, too, would happen quickly. As Apophis approaches, the stretching grows. As it passes the nearest point over the Atlantic, the force peaks. As it recedes, the disturbance fades. The entire surface story may open and close within just a few hours, leaving scientists to read the traces after the moment has passed. For a piece, the most important changes may be compressed into a very short interval: the adjustment in spin, the strain through the narrow neck, and, if they occur at all, the avalanches. It is almost as if the asteroid takes one long, silent breath while Earth's gravity tightens around it and then lets go. Spacecraft will be waiting to study that brief moment closely, and scientists will set the before beside the after with every instrument and model available. Yet the scale of that breath remains unknown. It may be no more than a faint sigh, barely visible in the data, or it could become a surface-changing shudder. The reason is simple and unsettling. The answer depends on the hidden interior of Apophis, the chapter no observer has yet been able to read. The flyby is the instant when that sealed page opens. If the inside is stranger, weaker, or more uneven than expected, the visible response could be far more dramatic. So the question becomes calm but urgent. What do researchers think is most likely? This is where the careful work of simulation takes over. Several independent groups have modeled the encounter in detail, building virtual rubble pile versions of Apophis from thousands of separate particles and then letting Earth's flyby play out inside the computer. Across those studies, one result appears again and again. The spin state of Apophis is expected to change, and not by an amount too small to notice. The asteroid will probably continue tumbling, but the rhythm of that tumble may be altered substantially. Depending on how its interior is arranged, the effective spin rate could fall to roughly half its current value, or rise to roughly twice it. The orientation of its rotation axis in space, known as the pole, is also expected to move. In the course of a single afternoon, Earth's gravity may revise a pattern of rotation that the asteroid has carried for ages. That idea matters because spin is not just a detail. It is one of the few outward clues to what a small world may be like inside. Still, this is also the point where caution is essential. It would be easy to let the drama of the encounter grow beyond the evidence, but the mainstream models do not predict a body being visibly crushed, folded, or bent. The actual distortion of the asteroid's shape, the stretching and squeezing of its material, is expected in most calculations to be extremely small, on the order of centimeters or even less. Much of that motion would likely be elastic, meaning the body yields slightly and then returns, rather like a stress ball recovering after the pressure is released. By the standard prediction, Apophis is not going to behave like wet clay. An observer drifting beside it would not watch its outline warp in any obvious way. The likely physical changes to the surface and overall form are delicate, not catastrophic. Put plainly, the encounter is not expected to destroy the asteroid. The leading expectation is a measurable spin change, accompanied by small, subtle disturbances. But subtle does not mean unimportant, and the most interesting part is where those disturbances gather. Recall the neck, the narrow waist between the two lobes, the seam that has been worth keeping in mind. When the models ask where the stress becomes concentrated during the passage by Earth, the answer repeatedly points back to that same region. The neck is where the tidal forces do their most focused work. It is the place where Earth's pull may briefly ease the compression that normally helps hold the two halves tightly together. In some simulations, that easing is enough to permit a slight but genuine rearrangement. One lobe may roll or shift a little against the other, while Earth's gravity loosens the grip that had kept them locked. This is a small motion in ordinary language. Yet for a rubble pile, it could be deeply revealing. It raises the quiet question of whether the asteroid's shape is held together firmly, or whether it is closer to a poised arrangement waiting for the right nudge. And there may be another effect, this time across the surface. The same tidal stress, combined with a modified spin rate, could trigger something scientists would very much like to witness: landslides. On a world held together so weakly, only a modest disturbance may be needed to set loose material in motion. A slight change in rotation changes the fine balance between gravity drawing grains downward and centrifugal motion tending to carry them outward. Tidal shaking could pass through the pile like a tremor. The result might be avalanches, slumps, or regolith slides, with loose surface material cascading across the asteroid and revealing fresher ground below. That buried material has been protected from space for an unknown length of time, and its exposure would make the encounter more than a change in motion. It would become a moment of renewal on the surface itself. In only a few hours, Apophis could partly resurface in front of our instruments. Modelers often describe these possibilities with careful language: small, limited, possibly negligible. Measured against the scale of a cinematic disaster, that restraint is justified. There is no predicted explosion, no shattering, no asteroid torn apart in spectacle, but the quiet phrasing can hide the historical weight of the event. What is being described is a planet altering the spin of an asteroid, shifting its pole, easing stress at the seam between its two halves, and perhaps setting off landslides that expose fresh material, all while we watch. Nothing quite like that has been observed before. Across the entire record of human science, we have not had such a direct view of a planet physically reworking another world during a single close pass. On a cosmic scale, the event may be modest. On a human scale, it could be unprecedented. And this is where the suspense truly lives. The most troubling part for scientists is not one particular forecast, but the breadth of the forecasts. Every simulation must make assumptions about the same hidden property: the interior. How is the mass distributed inside the asteroid? How much cohesion binds the rubble together? Is the neck tightly packed or only loosely held? Do the two lobes share similar density, or are they very different? Because those answers are not yet known, researchers run many possible interiors and the outcomes spread widely. A stronger, more tightly connected body produces the gentler version of the encounter, a modest spin change and little else. A weaker, looser, more irregular body allows the dramatic version, a major spin shift. Real movement at the neck, visible landslides, and a changed face. That uncertainty is the heart of the story. The models cannot tell us exactly what will happen. They can only map the range of what could happen. The choice, in a sense, belongs to Apophis itself, and it will reveal that choice only while the natural experiment is already unfolding. For 20 years, scientists have been asking what this asteroid is truly like on the inside. Earth's gravity will press the question, and the asteroid's response will be the answer. A large, surprising change would suggest an interior that is weak or unusual. A barely detectable response would point towards something stronger than its fragile appearance might imply. In either case, the close flyby is the instant when the hidden machinery of Apophis becomes a little less hidden. Its spin, its subtle sliding motions, and the behavior of that narrow neck will be the real readout of the experiment. Until then, the most important parts of the answer remain locked inside the asteroid itself. And because no model can fully watch that moment before it happens, a far more dramatic possibility has gained a life of its own online. It is an idea that the gentle, centimeter-scale simulations do not support, yet it is serious enough in spirit that we should not simply wave it away. The claim is that in 2029, the so-called God of Chaos might do more than deform. It might split. So let us take the strongest version of that argument, the version being repeated with the most urgency, and examine it carefully before deciding what it is worth. In that telling, Apophis is not a simple rock but a two-lobed body, joined through a slender bridge of material. That bridge, the argument says, has a critical thickness. Supporters of the scenario often place the dividing line somewhere around 30 to 35 meters. If the neck is wider than that, they say, it can endure the tidal pull during the flyby and keep the two lobes connected. If it is thinner, Earth's stretching force could overcome the joint, the neck could give way, and the asteroid could become two separate bodies. From there, the story becomes even more unsettling. Once Apophis is no longer one object. The fragments would not be identical travelers. They would have slightly different shapes, slightly different masses, and therefore slightly different paths. The most provocative step in the argument is that one piece, newly separated from the other, might pass through a gravitational keyhole, one of those extremely narrow routes that can set up a later impact, even though the original combined asteroid would have missed it. That is why the idea has such emotional force. It takes something already measured as safe and asks whether the thing being measured might change at the worst possible time. The question is not absurd, but it must be handled with great care. To be fair, the basic instinct behind the breakup scenario is not fantasy. It leans on real physics. Narrow connections really do concentrate stress, whether the object is a welded joint, a bone, a candy bar, or an asteroid made of loose material. In a structure with two larger masses joined by a thin middle section, the weakest region is often where failure would begin. Contact binary asteroids can, in principle, be separated by tidal forces. And there is good reason to think that some asteroid pairs, along with some of the stranger shapes we observe, may be linked to tidal disruption during earlier close passes by planets. So the broad idea is physically meaningful. A close planetary encounter can stress a rubble pile body at its most fragile point, and under the right circumstances, that body can be pulled apart. The people promoting the dramatic version are not inventing a mechanism from nothing. They are taking a real mechanism and pushing it to its most extreme setting. That distinction matters because it helps us avoid two easy mistakes. One mistake is to treat every alarming claim as nonsense. The other is to treat every real physical possibility as equally likely. Now, return to that proposed neck limit of around 30 to 35 me. There is a real principle hiding underneath the number. A neck's ability to resist being torn apart depends, in broad terms, on how much material is actually bridging the lobes. More cross-sectional area means more grains in contact, more self-gravity helping hold the lobes together, and more cohesion across the joint. A thicker connection can bear more stress. A thinner one has less material to share the load and can fail more easily. So, the concept of a threshold where a given tidal stress becomes too much for a given neck is not unreasonable. The trouble begins when that general idea is presented as if we already know the exact cutoff for Apophis. We do not know the width of the neck with the precision needed to place it confidently on one side of a sharp boundary. We also do not know its cohesion well enough, and the threshold depends on both the geometry and the material behavior. In other words, a legitimate physical relationship has been turned into a clean-sounding number that the available data cannot yet justify. This is where a calm reading changes the mood of the story. The danger is not that the physics is fake. It is that uncertainty has been made to look like a precise verdict. There is another point that the most dramatic versions of the story often leave out, and it changes the picture substantially. Even if we granted the breakup for the sake of argument, a separation at the neck would not resemble an explosion. There would be no blast, no spray of fragments, no violent cloud of shrapnel. If the two lobes, held together only weakly, managed to part, they would drift away from one another very slowly. perhaps at only a few centimeters s. With walking pace as an absolute upper limit and likely much slower, the image is less like a bomb and more like two boats on a still lake, quietly moving apart after the rope between them is released. For a long while, the pieces would continue along almost the same orbit, traveling side by side and separating by meters over hours. That slow motion is important because the keyhole part of the claim requires extraordinary precision. A fragment would have to be shifted by just the right amount, in just the right direction, to pass through a gravitational keyhole less than a kilometer wide, even though the intact asteroid has already been measured to miss the relevant keyholes by a wide margin. So the proposed chain has several links. The neck must fail, the fragments must separate in a particular way, and one fragment must receive just the right tiny orbital change. Each step narrows the odds further. This is not impossible in the logical sense. It is not like asking for a square circle, but it is improbable in the way that a coin landing on its edge twice would be improbable. The more carefully the sequence is laid out, the less it resembles a looming expectation, and the more it resembles a stack of unlikely coincidences. That is why the honest judgment on the breakup scenario should not be a theatrical yes or a careless no. A better answer is that the idea is grounded in real mechanics, but the specific feared outcome is very unlikely. That is more satisfying than either the disaster version or the dismissive version, because it allows the physics to be real without allowing fear to inflate it beyond the evidence. The keyhole twist, to be clear, is clever. It is also unsettling, because it finds a vulnerable seam in the way we talk about certainty. The reason Apophis became reassuring is that the trajectory of the combined body has been measured with enough precision to show that it misses every dangerous keyhole. But that statement applies to one object following one path. If the object somehow became two fragments following two paths, then strictly speaking, the old clearance would no longer be the full calculation for the new situation. Each piece would need to be evaluated on its own. That is the thought that lingers. What if the object already cleared by the measurements became fragments that had not yet been cleared? It is an uncomfortable question precisely because it begins from a real logical point. And this is where calm space can do its most useful work. Take the frightening version, slow it down, compare it with the actual science, and ask where it truly stands. At the moment, it stands as a physically conceivable but highly constrained scenario, one that deserves careful modeling rather than panic. The most careful simulations, including the particle-by-particle models that treat the asteroid as a rubble pile, do not point toward Apophis splitting open. What they mostly show is much quieter, deformation measured in cm, behaving elastically, as though the body bends, settles, and then largely recovers instead of tearing apart. The strongest stress gathers around the neck, and that matters because the neck is the place where the two lobes meet and where small shifts could be most visible. It may move a little. The lobes may ease or roll against one another by a slight amount, but a clean separation into two independent pieces is not what the physics indicates for a 300 meters object with this shape passing Earth at 31,000 kilometers. Earth's gravity will certainly tug on it. The pull is real and significant. Yet the models do not make that tug strong enough to rip such a body in two. In that range of outcomes, breakup sits far out on the unlikely edge, not near the expected center. And the keyhole concern depends on that unlikely breakup happening first, which makes it a small possibility layered on top of an already improbable one. Added to this, an impact has been ruled out for 100 years for the object as it is currently understood, and credible modeling does not suggest that conclusion is about to overturn. Still, this is where the calm story becomes more delicate. Scientists cannot entirely relax, and it would be misleading to call the matter empty of uncertainty, because every reassuring statement depends on models, and those models depend on assumptions about the interior, the very region no telescope can directly inspect. When researchers say a breakup is not expected, the careful version of that statement is that breakup is not expected if the interior has roughly the strength they believe it probably has. That is a reasonable assumption, but it is not direct knowledge. There is also a narrow, genuinely scientific pocket of remaining uncertainty. Before 2029, Apophis' exact trajectory could, in principle, be shifted very slightly by the gravity of another small object that has not yet been detected. This is not a hidden warning or a dramatic claim. It is simply the honest boundary of what can be known in advance. The reassurance is powerful, but it is not absolute, and the difference between those two words is where unease naturally gathers. That unease is not just abstract caution, because close planetary encounters really can alter small bodies. Across the asteroid population, astronomers have identified pairs, two separate asteroids moving around the Sun on nearly identical orbits, apparently descended from one parent object that came apart. Other asteroids seem to have been spun up until they shed some material. Evidence has also accumulated that the surfaces of many near-Earth asteroids have been renewed, their older weathered layers disturbed by earlier close approaches to Earth and other planets. So the gentler version of the Apophis expectation, shaking, shifting, resurfacing, is not merely a computer exercise. The solar system appears to have performed variations of that process many times. The real question is scale, and scale depends on what lies inside. A compact, well-bound body might pass through the encounter with only modest disturbance, while a weaker, loosely packed one could be rearranged in a more meaningful way. That is why Apophis is such an important natural test. We do not yet know which kind of interior it has. The lingering uncertainty about a possible gravitational nudge deserves careful attention as well, precisely because it is the sort of sober detail that can vanish between alarmist claims and casual dismissal. Researchers have noted that, in principle, Apophis could have its path adjusted by a close gravitational interaction with some undetected asteroid before 2029, perhaps a small dark object crossing nearby. Any effect would be tiny, and it does not bring back the impact scenario, but it does remind us that predictions about exactly where Apophis will be, and therefore exactly how strongly Earth will stress it, assume that all relevant influences have been accounted for. They almost certainly have, but almost is not identical to certainly. Responsible science leaves room for that distinction. This is not fear-mongering. It is the texture of a real forecast about a real object moving through a crowded solar system. Put the pieces together, and the emotional balance becomes easier to understand. Here is an object with an unseen interior, traveling outside the zone of certain destruction, but within a region where unusual effects can occur. It has a known weak point that should receive the strongest stress, and a small but legitimate residue of uncertainty sits above the calculation. None of this amounts to a catastrophe. It does, however, create suspense. Researchers are not preparing for disaster. They are preparing for the possibility of surprise. In a science built around prediction, that kind of surprise can be both uncomfortable and deeply compelling. One memory shadows the entire discussion, because it remains the closest real example of the dramatic event people imagine. In 1994, the comet Shoemaker-Levy 9 did the thing some fear Apophis might do. It passed too near Jupiter, and Jupiter's immense tidal forces pulled it apart. The comet became a train of more than 20 fragments, famously described by astronomers as a string of pearls across the sky. On its following pass, those pieces struck Jupiter, one by one, carving scars into the giant planet's clouds that were larger than the Earth. Humanity watched the sequence unfold. It showed, beyond speculation, that a planet's gravity can tear a body apart and leave it stretched into a chain of fragments. That part is not imaginary. It has happened. The event is worth pausing over because it revealed the power of tidal forces with extraordinary clarity, and because so many people were able to witness the aftermath. The comet had actually been disrupted during an earlier close approach to Jupiter before it was discovered. By the time astronomers found it in 1993, it was already shattered into more than 20 pieces, laid out in a line. When the Hubble Space Telescope observed it, the image quickly became iconic. Bright, icy fragments stepping through the darkness, each surrounded by its own faint haze, the famous string of pearls. For more than a year, people knew those fragments were destined to fall into Jupiter. Then, over several days in July of 1994, they arrived, one after another, hitting the giant planet at tremendous speed. Each collision raised a dark plume of debris, and the marks left in Jupiter's clouds were so vast that some exceeded the width of the entire Earth. They remained for months, visible even in backyard telescopes. That week changed the way our species thinks about the sky. For the first time, humanity did more than discover the aftermath of a solar system collision. We anticipated one, marked the calendar, and then watched the event happen when it was supposed to. That changed the conversation. Impacts were no longer just scars left in ancient crater fields, but an active force, still at work, still capable of altering worlds in the present. In the years after that spectacle, the effort to search for hazardous asteroids gained a new seriousness, both in funding and in public will. A comet had come apart beside a planet and struck it in fragments larger than continents, and the people watching from Earth could no longer treat danger from above as an abstraction. The famous string of pearls remains one of the defining images for anyone who studies these events. It is also the image that naturally returns when people hear tidal forces mentioned alongside a balobed asteroid. So when online speculation borrows that memory and tries to attach it to Apophis, the impulse is understandable. It was, after all, the most dramatic display of tidal disruption we have ever seen in real time. But memory is not the same thing as prediction, and this is where the comparison must be handled carefully. Shoemaker-Levy 9 was a delicate comet, trapped by the strongest planetary gravity well in the solar system, then torn apart over multiple close approaches. Apophis is a stony rubble pile, passing once and quickly by a much smaller planet, outside the region where tides alone would be expected to pull it to pieces. The pearls show what can happen at the far edge of violence. They do not by themselves tell us what will happen in this case. That is why Shoemaker-Levy 9 matters here, not because Apophis is the same story, but because the difference is the point. Jupiter is enormous, more than 300 times the mass of the Earth. With a tidal reach our planet cannot imitate, the comet did not merely skim past Jupiter and leave. It was caught, forced into a tightening path, and gradually dismantled. Apophis, by contrast, is making one rapid encounter with a far less massive world before moving on. Earth is not Jupiter, and a near pass is not the same as a deep fall. The pearl chain image is real, and it deserves its power. Yet, it belongs to an encounter far more extreme than the flyby expected in 2029. A calmer reading does not require us to imagine disaster, but it also does not ask us to wave the question away. The wiser position is to remain inside the uncertainty. The tension around Apophis is not that it is expected to disintegrate, it is that the encounter itself will be the only test precise enough to show what actually happens. And that leads to the most practical question in the whole story. When this one natural experiment finally runs, who will be watching? And with what level of detail? The answer could determine whether we come away with a deep record of the event or only a fleeting glimpse. Part 7. The Machines and the 2 Billion Eyes. Across most of solar system history, close planetary encounters have happened without witnesses. Asteroids have swept past planets for billions of years, sometimes altered by gravity, and almost all of those moments vanished without measurements, images, or observers. What makes 2029 so different is not only the closeness of the past, but the fact that we will be ready for it. We will not simply look up in surprise. Telescopes, spacecraft, instruments, and human observers will all be focused on the same object at the same time. That turns a celestial spectacle into something closer to a controlled investigation, even though nature is the one setting the conditions. Two spacecraft in particular make the moment scientifically powerful. The first carries one of the most remarkable second lives in space exploration. Many will remember the mission named OSIRIS-REx. The NASA spacecraft that traveled to Bennu, reached its surface, collected material, and sent that sample back to Earth in a capsule that landed in the Utah desert. Its original assignment could have ended there. The spacecraft had already succeeded, but it remained healthy. It still had fuel, and it was still traveling through space. So NASA gave it a new identity and a new destination. Now called AUKUS Apex, its purpose is to pursue Apis. A machine that had already demonstrated it could rendezvous with one rubble pile and make contact with its surface is now on course to meet the most famous asteroid of this era. Even the timing of its arrival has a quiet elegance because it reflects how carefully the orbit has been measured over 20 years. OSIRIS Apex is set to reach Apis around the April 2029 close approach. As the asteroid and spacecraft sweep past Earth, the spacecraft passes roughly an hour behind it. Then it uses Earth's gravity as a slingshot, gaining the assistance needed to catch up with Apophis a little more than a week later. After that, the brief chase becomes a long study. For about 18 months, the spacecraft will travel beside the god of chaos, using cameras, spectrometers, and a laser altimeter to map the terrain, measure the asteroid's shape in fine detail, examine the chemistry of the rock, and monitor its rotation. In a story built around what we cannot yet see, that sustained presence may be the difference between guessing at the asteroid's behavior and watching it unfold. The most extraordinary act planned for OSIRIS Apex, however, comes from something it learned at Bennu, and it may be the closest we get to probing beneath the asteroid's skin. The spacecraft is intended to descend toward the surface until it is about 5 meters above the ground, close enough to feel almost intimate on the scale of spaceflight. Then it will fire its thrusters downward. Those engines will blast the loose upper layer, stirring and sweeping material away on purpose. The aim is to uncover fresher matter just below the exposed surface, material that has been protected from the harsher effects of space weathering, and then study what appears. In the context of Apophis, that gesture matters. We have been circling the same central problem. The inside of Apophis is effectively a black box. OSIRIS Apex cannot open the entire body, but it may disturb one small patch enough to reveal a little of what lies under the outer coating. That is not a casual maneuver. It is a deliberate attempt to let the asteroid answer back. It is also easier to trust the plan when we remember the spacecraft's earlier work. As OSIRIS-REx, it spent years around Bennu, charting boulders, selecting a sampling site, and carrying out one of the most delicate operations ever attempted near an asteroid, descending, touching the surface, and collecting a sample. That material, amounting to a few hundred grams of pristine asteroid, returned in a capsule and parachuted into the Utah desert in the autumn of 2023. It was the first American asteroid sample ever brought home. So, this next chapter is not based on an untried idea. It is a second use of a spacecraft that has already shown, in practice, how close it can come to a rubble pile and still do careful science. The mission being sent onward to Apophis is not an untested idea drawn on a clean sheet of paper. It is the same proven spacecraft, carrying the same instruments, guided by the same team that has already approached one rubble pile, touched it, and brought material back to Earth. So when mission planners describe OSIRIS Apex flying within only a few meters of the surface and disturbing the regolith, they are not speaking in abstractions. They are adapting a maneuver this particular spacecraft has, in essence, already performed. Its arrival, however, is governed by the orbit that has taken 20 years to measure so carefully, and that makes the dance especially worth imagining. Osiris Apex cannot simply pull up beside Apus as the asteroid rushes past Earth. The speed, direction, and timing cannot be matched in a single instant. Instead, the spacecraft is planned to sweep through the close passage just behind the asteroid, following by only about an hour as the whole geometry passes Earth. Then, our planet's gravity becomes a slingshot, the familiar kind of free assist that has redirected and accelerated spacecraft across the solar system for decades. With that boost, Osiris Apex bends its own path until it can catch Apophis a little more than a week later. After that, it settles into formation and remains there for roughly a year and a half. A patient witness, moving beside the god of chaos through the quiet months after the tidal squeeze, watching how the shaken body relaxes and settles. That long companionship matters, because the most revealing changes may not be captured in a single dramatic moment. They may unfold slowly, as the asteroid responds to what Earth has done. The second spacecraft completes the larger experiment, and it carries a heritage of its own. Europe's Ramses mission draws from hardware and design experience gained on an earlier European mission to another asteroid system. So, like Osiris Apex, it is not beginning from nothing. Its role is different and just as essential. It is there to see the before. By reaching Apophis around February of 2029, roughly 2 months ahead of the encounter, it can take measured, careful observations while the asteroid is still in its undisturbed state. That becomes the baseline. Then, Ramses rides along through the flyby and records what comes afterward. Among its instruments is a Japanese-built thermal camera designed to read temperature across the surface. Those temperature patterns tell us how the ground holds heat and releases it, which, in turn, points to whether the surface is loose or compact, fine-grained or strewn with boulders. And here the story folds back into one of its earlier threads, the Iovsky effect. That faint, heat-driven push that helped refine the understanding of Apophis of impact. The same thermal mapping that reveals the surface also improves the estimate of that subtle push, tightening the orbit still further. In this investigation, each part feeds the next. Heat helps describe the surface. The surface improves the orbit. The orbit allows the spacecraft to be aimed, and the spacecraft, in turn, helps read what lies inside. Ramses will not be alone in that task. The European Space Agency, working with the Japanese Space Agency, is building this second mission with a separate but equally important purpose. It is intended to launch around 2028 and reach Apophis in February of 2029, about 2 months before the close approach. That timing is not incidental, it is the heart of the design. Ramses arrives early so it can examine Apophis before Earth's gravity disturbs it. It will measure the asteroid's shape, spin, surface, and exact state, building a detailed picture of what Apophis is like before the encounter changes the conditions. Then, during and after the passage, it can watch for the differences. The thermal infrared imager contributed by Japan adds another layer by measuring the surface temperature and helping reveal both the nature of the outer material and the way heat travels through it. This before and after structure is what turns the event from a rare spectacle into a controlled, natural experiment. If we only saw a pace after the flyby, we could describe what it looked like, but we could not confidently say what had changed, because the starting point would be missing. With Rams on station 2 months early, measuring the spin, the shape, and the surface in detail, the starting condition is recorded. Then, Earth applies the force. Then both spacecraft measure the aftermath. The difference between those two records becomes the answer to the question that has been building for 20 years. It is the readout from the experiment itself. We are not merely watching a puff be squeezed by Earth's gravity. We are preparing to measure how it responds, and from that response, we may begin to infer what it is made of inside. One more set of instruments will take part, larger in number than all the others, and, in its own way, just as important. They require no launch vehicle and cost nothing to build. They are human eyes, roughly 2 billion of them. While the spacecraft perform the precise science, people across Europe, Africa, and Western Asia will be able to step outside on that April evening and see Apophis without a telescope, a moving point of light brighter than the stars of the Big Dipper, crossing the sky during a single night. For once, in the long and strange history of humanity's relationship with the objects that share our solar system, this will not be an event many people first encounter as a report released the next morning. It will be something they can experience directly, in real time, by looking up as a piece of the early solar system passes beneath our satellites. Beyond the naked eye crowds and the two spacecraft, another layer of observers will be waiting, the professional observatories on Earth. Their instruments will turn toward Apophis as it sweeps past. Powerful radar dishes will send radio waves toward it and use the returning signal to read its shape and spin at the moment of closest approach, applying the same method that first revealed its two-lobed form, now focused on the asteroid during the very hours when it is being stressed. Telescopes around the world will monitor its changing brightness as it tumbles, searching for the faint variations that could indicate a shifting spin or newly exposed surface. Between the ground-based observatories, the spacecraft, and the unaided human eye, almost every aspect of that evening may be captured. It is as if every kind of vision we possess is being brought to one shared moment. That shared witnessing is not a small detail at the edge of the science. It changes the feeling of the entire encounter. For most of human history, the sky was something that happened above us, something interpreted afterward through fear, myth, and much later through instruments. On the night of the 13th of April, 2029, 2 billion people and a small fleet of robotic explorers will watch the same experiment unfold at the same time, with some understanding of what it is and why it matters. The spacecraft will read the spin, the surface, and the hidden interior. The observatories will extend that measurement from Earth. The human eyes will carry the memory, and all of them will be turned toward the same question with which this story began. All through this story, one quiet question has been vibrating beneath the surface, waiting for Apophis itself to make the answer visible. What is really hidden inside the God of Chaos? Soon, we will have the strongest chance we have ever had to learn that, and the importance of doing it well extends far beyond a single asteroid passing Earth. Part 8 brings us to the black box at the heart of the God of Chaos. If we gather the clues in one place, the picture becomes unsettling in its clarity. There is the strange double form, two lobes connected by a narrow, vulnerable neck. There is the density, much too low for a body made of solid stone. There is the possibility that as much as 40% of it may be empty space. There is the way it tumbles, a motion that does not behave like a smooth, uniform rock, but instead hints at an interior that is uneven, clumped, and complicated. These observations were collected by different tools across different years. Yet they all lean toward the same conclusion. Apophis is not a single mountain of stone drifting through space. It is most likely a rubble pile, a weakly bound collection of material held together by an extremely gentle grip. And the most important part of it, the structure inside, the way the pieces are arranged, and how strongly they cling together, has never been directly measured. At present, we cannot reliably predict it. That is why the word nervousness matters here. It does not mean fear that Apophis is about to strike Earth. It is not going to do that. Its orbit is clear for a century, and this entire story would be meaningless if it were built on pretending otherwise. The unease comes from something subtler, a single, unrepeated natural experiment on the most studied, dangerous asteroid in human history, with no practice run and no opportunity to try again. The result depends on the one feature still hidden from our instruments. In that sense, Apophis is less like a known object passing by and more like a sealed instrument case about to be shaken by gravity. For scientists, This is both thrilling and uncomfortable. They have designed models, gathered observations, and prepared spacecraft. Yet the outcome remains genuinely unknown. In a discipline built around prediction, that kind of uncertainty is rare. It may be exactly why this encounter feels so alive. It is also worth pausing to address the louder, more suspicious version of the story, the one that suggests these details were withheld, that contradictions were buried, and that the public is only hearing about them because someone connected points that powerful people preferred to leave apart. That framing can be tempting, and it deserves to be answered carefully rather than dismissed. But the plain truth is that this is not what happened. The radar-derived shape, the unusually low density, the rubble pile interpretation, the strange tumbling motion, the expected changes in spin, and the possibility of stress building at the neck were all discussed openly in scientific literature. They were presented in public planetary defense meetings. In fact, these very uncertainties are a major reason spacecraft are being sent to study Apophis at all. The irregularities were not hidden in the shadows. They were the central subject of the research. What makes them feel secret is something more ordinary and perhaps more revealing. They were written in the precise, technical language of a specialist field that most people never have reason to read. The information was available, but it was not shaped into a story that most listeners could easily follow. That is part of why Calm Space exists, to bring the difficult, quiet language of space science into a form that can be understood without losing its wonder. And in many ways, the real account is far more compelling than any cover-up. A cover-up would imply that someone already has the answer and is refusing to share it. The reality is stranger and more humbling. No one knows, not the agencies, not the modelers, not this narrator, not anyone. The most intensely studied dangerous asteroid in human history remains, at its core, a closed box. The only key that may open it is a planetary encounter that still has to unfold in real time. There is no concealed solution, because there is no solution yet to conceal. There is only an open question, suspended in space and time. The honest weakness in our confidence is not a conspiracy either. It is the fact that the interior has not been measured, and that there remains a small, real possibility that an object we have not yet seen could give Apophis a tiny gravitational nudge before the encounter. That is not a hidden catastrophe waiting to be exposed. It is simply the edge of knowledge. Every frontier has an uneven boundary, and this one passes directly through the heart of an asteroid. From there, the importance of 2029 becomes much larger than one rock on one night. Scientists are not merely anxious. They are excited because this event is a free rehearsal for a skill humanity may one day need with absolute seriousness. Somewhere in the dark, on an orbit that may not yet be fully mapped, there could be an asteroid whose path matters to us in a way that cannot be ignored. If we ever need to deflect such a body, if we ever have to give it a careful push away from a collision course, the most important question may not be its size alone, or even its surface appearance. It will be what it is made of inside. A rubble pile cannot be treated like a solid boulder. Push a loosely bound heap in the wrong way, or with too much force in the wrong place, and the result may not be a clean deflection. It could break apart, leaving several pieces to arrive separately. That possibility is why the interior matters so deeply. With a pulse, Earth's gravity will do the squeezing while our instruments watch, offering the first real lesson in the hidden mechanics of such bodies. It is a lesson paid for by an encounter rather than by an impact. That distinction matters. A rehearsal offered freely by gravity is precious. A real performance, if one ever comes, would not offer the same calm margin for learning. We have already taken the first deliberate step toward learning how to push back against the sky, and it shows exactly why the unseen interior cannot be ignored. In 2022, NASA sent a spacecraft called DART into a small moonlet named Dimorphos, which orbits a larger asteroid, deliberately striking it at thousands of km/h. This was the first time humanity intentionally altered the orbit of a celestial body, and the attempt succeeded. Apophis changed its orbit by a measurable amount. Yet the deeper lesson was not as simple as impact equals motion. Apophis turned out to be a loosely held rubble pile, and when DART struck it, the result was not a tidy crater punched into firm ground. The body reacted almost like something soft and granular. Material burst outward, sending a large plume of debris into space and creating a tail of rubble behind it. That escaping material produced recoil, and the recoil pushed Apophis more strongly than the spacecraft's impact alone would have done. In other words, the weakness of the moonlet was not a minor detail. It transformed the entire response. This is the quiet warning inside a successful test. If one day we need to nudge an asteroid away from Earth, its behavior will depend on its interior nature. Strike a solid rock, and it responds like a solid rock. But strike a fragile heap, and the story may become far more complicated. Strike a loose rubble pile, and the result may not look like a clean shove at all. The energy could vanish into shifting grains, burst through the body like a splash, or, in the worst case, split the object into several fragments that continue onward along slightly altered tracks. A single danger could become many. That is why any serious deflection plan begins with a question that is frustratingly simple. What is the asteroid like on the inside? After all this, that hidden interior remains the hardest part to know from a distance. So, when Apophis passes close enough in 2029 for Earth's gravity to squeeze and disturb it, the watching will not be idle curiosity. Its changing spin, the possible movement of its neck, and the slipping of material across its surface may become clues to a structure we cannot otherwise inspect. In a quiet sense, Earth will be providing an experiment without charge, one that might otherwise demand a dedicated mission, or be learned under far more terrible conditions. This is why researchers speak of the 2029 encounter with the kind of awe once reserved for a rare eclipse. It is not merely close, it is a rare alignment between preparation, visibility, and scientific need. Years of warning have placed a famous object within reach of questions that usually remain sealed away. The kinetic impactor, the intentional strike demonstrated by DART, has shown one possible method, a slower and softer idea. The gravity tractor would keep a spacecraft near an asteroid and use its tiny gravitational pull to draw the object off course over many years. Yet no technique is better than our knowledge of the thing being moved. Apophis may soon offer precisely that missing lesson, and the importance of that possibility is difficult to overstate. Step back, and the story becomes almost philosophical. We often picture the solar system as an architecture of solid things, planets, moons, and rocks crossing a vast emptiness. But the small bodies have complicated that image. Asteroids such as Apophis, Itokawa, and Bennu suggest that many of these objects are not firm stones in the familiar sense. They can be loose collections, fragile heaps held together only weakly, more like gathered debris than single mountains. That realization changes the emotional texture of the sky. We are moving through a neighborhood where loosely bound material follows long paths around the sun, sometimes drawing near. In 2029, one of those debris piles, carrying the name of the Serpent of Chaos, will come close enough for our planet to take hold of it gravitationally. In that brief grip, it may reveal something of its true nature. There is also a deeper timescale inside this encounter. Apophis is not only a possible hazard, and not only a convenient experiment, it is also a remnant from the beginning. Objects like it are leftovers from the raw material out of which the planets formed more than 4 billion years ago, material that was never absorbed into a larger world. When scientists examine the composition of Apophis, with its stony mixture resembling meteorites that fall to Earth, they are studying matter related to the substance that made the ground beneath us. The rubble pile passing above the Atlantic that night is, in a real way, a surviving piece of the construction site from which our own world emerged. To infer its inner arrangement is to glimpse a page from the solar system's earliest chapter, a chapter usually locked inside bodies too small and too remote to probe directly. Perhaps that is the thought worth carrying longer than any single figure. We have become a species capable of charting this object's route for the next century. We can say where a mountain of rock will be on a particular Friday evening 4 years from now, after it has traveled hundreds of millions of kilometers around the sun, and we can narrow that prediction down to the kilometer. That is an astonishing kind of power. And still, in the same breath, we must concede that its interior remains unknown. Our best forecasts about how it will respond carry a quiet uncertainty. The answer will not come because we solved every detail in advance. It will come because we watch the encounter unfold and see how the object behaves. There is a strange humility in that. Humanity has assembled the most precise celestial map it has ever possessed, and that achievement has brought us to something like a closed box. We cannot open it by thought alone. We have to wait. The tension between our precision and our blindness is what gives this event its force. It helps explain why those who study Apophis are watching the calendar move toward 2029 with a feeling that seems to sit between anticipation and unease. They are not panicking, they are preparing. In effect, they have organized one of the most careful observations ever aimed at a single rock, and now they are waiting to see whether the god of chaos supports their expectations or disturbs them. Even the fact that we can prepare at all is close to unprecedented. For most of human history, visitors from the sky arrived without notice. There was a flash, a blast, perhaps a crater, and only afterward the slow attempt to understand what had occurred. Knowledge came after impact, when it was already too late to do anything except endure the result. Apophis is different in a way that deserves to be felt. It was seen coming 25 years ahead of time. It was debated, measured, removed from the list of immediate threats, and then transformed into a planned scientific event. Perhaps for the first time, we are meeting one of these close celestial visitors on terms we have chosen, with instruments ready, attention focused, and questions prepared before the moment arrives. That would have seemed unimaginable to our ancestors. Something once interpreted as an omen can now become an experiment carried out deliberately. Yet this power has an edge, and that edge is why the subject is not merely academic. Somewhere beyond our present certainty, on an orbit we may not yet have drawn, there is very likely an object that will not miss, not Apophis, but something else, in some later year that no one has marked yet. When that time comes, the lessons drawn from 2029 may matter intensely. Every clue taken from this rubble pile, how it holds together, how it shifts, how it might break, could separate a successful deflection from an attempt that turns one approaching body into a swarm. The serpent that passes by is, in this sense, instructing us for the serpent that may not. That is why scientists are not simply intrigued. They understand that gravity is giving us a lesson at no cost, and it may be one we cannot afford to waste. So return, once more, to the image where this journey began. The 13th of April, 2029, a Friday evening over Europe and Africa. Darkness gathers, the first stars come out, and then a moving point appears where no ordinary star should be, climbing through the sky. Brighter than the handle of the Big Dipper, crossing the heavens faster than anything up there seems meant to move. 2 billion faces look upward. Nearby in the darkness, 2 spacecraft keep formation beside it. For several quiet hours, a world and a wandering shadow will cross paths again, as they have done innumerable times across the solar system's deep past. Yet this encounter is different, because for the first time, human eyes may be prepared to notice what the meeting means. Until the moment arrives, the answer remains hidden. Even the most celebrated asteroid ever detected is still, in many ways, sealed to us, waiting for Earth's gravity to reveal what observation alone has not. for 22 years. This serpent has returned through space since it was first spotted from a mountaintop in Arizona. In 2029, it will pass close enough to feel almost within reach. What matters then is a delicate question. When our planet tugs at the god of chaos, will we be ready to interpret its response, or will it murmur once above the dark Atlantic and carry most of its secret back into the night?